Today we're going to be looking at graphs of the cosecant and graphs of the secant. They're actually pretty straightforward graphs since we already know how to graph the sine and the cosine. So the main idea behind these graphs is just to graph the sine and the cosine and then think about what happens at the reciprocal values. In other words, when you flip the cosine or you flip the sine upside down. So let's take a look at that. So starting with the sine. You'll notice that along the sine graph, there's many places where the sine equals 0. Well, if you flip this upside down, you'd get 1 over 0. And so all the places where the sine equals 0, you're going to have a cosecant that's undefined. So I'm going to mark all these places where the sine equals 0. Those are all the places where the cosine is going to be undefined. Okay. So now in between all these red dashed lines where the cosecant is undefined, that's where the cosecant is going to exist. And basically the cosecant is a flipped upside down. It's a reciprocal value to the sine. And it lives in between the dashed lines, touching the sine at exactly one point, and then heading off toward positive and negative infinity. So I'm just kind of drawing these sort of parabola shapes. I'm trying to make it so that they tend toward or head toward the red dashed lines, those asymptotes. And I'm trying to make it so that they touch at exactly one point where the sine wave would be. Good. And I don't have to graph very many of them, but I'm graphing one for each of the sine waves that I have here. So you'll notice that for the cosecant, that's the blue graph, it's in between these red lines, right? And these red lines were the zeros of the sine. One thing we notice about the cosecant is it doesn't have any zeros. The other thing we notice about the cosecant is that it's stuck between the zeros of the sine. And since the sine hits at 0 every pi, that makes the period of the cosecant pi. So we also notice that because the sine hits 0 at every pi, that's where my red vertical asymptotes are. And I don't know if you can see this, but they're at pi, 2 pi, 3 pi. Right? It's basically all multiples of pi. Right? Okay, so dot, dot, dot. So now let's look at this graph now that we've had it graphed. What is the domain and what is the range of this function? Well, the domain, remember, is the x. So what are the x values that we have here? Well, we basically have everything except. So remember, this means x such that x is not equal to, and then it can't be equal to where we have these red dashed vertical asymptotes. So we'll put not equal to multiples of pi. That's going to be my domain. Okay, we'll come over for the range. The range, remember, is asking you about the y values. Our y values basically can touch the lowest value of the sine, and they can touch at the highest value of the sine, but they can't be anywhere in between those two things. So the y values are either going to be less than -1, which is the smallest value for the sine, or greater than 1, which is the largest value for the sine. Okay, so let's go down to the last part. Why is the cosecant undefined at these asymptotes? Well, remember, the cosecant is equal to 1 over sine x. And sine x equals 0 at multiples of pi, right? Remember, 0, pi, 2 pi. So if you take sine x and you stick it equal to 0 in this denominator down here, then you're going to have an undefined value. All right, so that's what the cosecant looks like. And as you can see, it's basically just built by first kind of sketching out the sine. All right, let's go down to the secant. All right, here's the secant. Now the secant pretty much works the same way as the cosecant. It's based off the cosine, and here's a cosine graph. And we can see at the cosine graph that the cosine graph goes up and down, and that the cosine graph also has places where the cosine graph is equal to 0. So we put those in as our asymptotes. Okay, and put those in. These ones are a little harder to see where the asymptotes are. Okay, this one's at pi over 2. This one's at 3 pi over 2. This one's at 5 pi over 2. This one is at, oops. This one is at 7 pi over 2. I hope that you can see a pattern that basically the vertical asymptotes are all at odd multiples of pi over 2. Okay, dot, dot, dot. So odd multiples of pi over 2. Now, if it's between pi over 2 and 3 pi over 2, so that's 90 degrees and 270 degrees, that means that this value right here, the period, is pi. So same period as the cosecant. And again, this period, this function's not going to have any zeros. Okay, so now let's graph the secant. Same as before, the secant is built off the cosine. So it's touching at one point here and then tending toward these asymptotes, going toward positive infinity on top and negative infinity on the bottom. Okay, here we go. We'll do a couple more. Okay, so now let's do a couple practice problems where we're graphing the cosecant and the secant. The idea for graphing the cosecant and the secant is to use what you know about transformations for sine or cosine. So remembering when we did this, that A was the amplitude, B was the frequency, it changed the period, C was the phase shift, and D was the vertical shift. If we can know what this A, B, C, and D do for the sine, then we can graph the sine and then base our cosecant off of that graph. And that's exactly what we're going to do. So if I'm going to be asked to graph this guy, y equals 2 cosine 2x, I want to start by graphing this guy, y equals 2 sine 2x. So let's think about what this guy looks like. Y equals 2 sine 2x has an amplitude of 2. It has a frequency of 2. And that means the period is going to be 2 pi over 2 or pi. So let's graph this now. Okay, it's got a height of 2 and a depth of -2 down here, and the period is pi. So every 6 boxes, I'm going to mark this off. 6 boxes, 6 boxes. Okay, now let's graph the sine. Okay, so the sine's going to be a hill and a valley, a hill and a valley, a hill and a valley. And I'm going to stop there. I could keep going, but we only probably need to graph a couple of these. Okay, and then remember that the cosecant is undefined wherever the sine is 0. So wherever the sine has a 0, so here and here, here and here, all of these zeros, if I flip that and make it 1 over the sine, all of these become undefined. So these become my vertical asymptotes. I mark those. And now I can come back and I can graph my cosecant. So the cosecant has like a parabolic shape. It touches the sine at one point. It approaches the asymptotes on both sides and heads off toward positive and negative infinity. Okay, so try to keep them in between your asymptotes there. Now I might want to come back with my eraser and just kind of tap out the sine a little bit, make it a little bit more of a dashed. Okay, just so he doesn't take prominence in my graph. There, that looks perfect. So that's cosecant, 2 cosecant 2x. All right, let's look at the next one. So in the next graph, we're also going to be graphing a cosecant, but this time we're going to be graphing it with a sine that has a phase shift of pi over 3. So let's start by graphing this guy right here. So what we know about that graph is that the amplitude is 1. The frequency is 1, so that makes the period just plain old 2 pi, right? So 12 boxes. And the phase shift is going to be pi over 3, which remember is going to be 2 boxes because it's 2 times pi over 6. So we'll start by phase shifting back 2 boxes. And then we'll count over 12 boxes for the period. So 2, 4, 6, 6. All right, let's see what we have so far. All right, so the period is 2 pi. So that's 1, 2. There's the sine. 1, 2. Just like before, I'm going to mark all the places where the sine equals 0. Okay, each one of these places where the sine equals 0 becomes an asymptote for my cosecant. So now I can draw my cosecant. He's going to live right inside the asymptotes, touching the sine at exactly 1 point. There you go. These ones are looking pretty good. And I'm done. Okay. So there's cosecant x plus pi over 3. All right, let's look at the last one. The last one's going to be a secant. So nothing tricky about this problem. We just graph a cosine instead of a sine. So let's see what that would look like. First of all, we notice that this has an amplitude of -3. So I'm going to go up 3 and down 3. Now before we were using every 2 boxes equaled 1, but because now we're not really interested in the sine or cosine, I'm more interested in the cosecant and the secant, I'm letting each box on the y-axis equal 1. That way my cosine and sine are pretty short, and it leaves more room for me to draw the cosecant and the secant. Okay, so on this problem we had an amplitude equal to 3, and then we have a frequency equal to 1/2, and that makes the period equal to 2 pi divided by 1/2. That makes the period equal to 4 pi. So let's take a look at what this would look like. Okay, so the period is going to equal 4 pi. Oh boy. All right, so this is an upside down cosine. So it's going to start down here, and then the period is going to be 4 pi. So let's see if I can count these boxes over correctly. 1, 2, 3, 4, and 6, and 6, and 6, right about there, looks like. Okay, which means about halfway through it's here, and then here, and here. All right, that looks good. All right, so here's my cosine. So notice that it's upside down, and because it's upside down, I started at the minimum instead of at the maximum. And since I'm not really interested in cosine, I'm interested in secant, I'm going to mark the vertical asymptotes where the cosine is equal to 0. Okay, so that's going to be here at pi, and here at 3 pi, and then here at -pi. And you don't have to mark those, but I'm just marking them to show you where they're at. Now we can graph the secant. So it's going to be here, and here, and it looks like we're not really going to get very much to graph on this side, but then one over here. And that's what -3 secant x over 2 looks like.